this video, we'll talk through the periodicity topic from Unit 1 of Higher Chemistry. By the end of this video, you should be able to explain the trends in melting and boiling points, be able to explain the trends in covalent radii, explain the trends in ionization energy, and explain the trends in electronegativity. We will need to remember some things from previously in chemistry, one of which is that the elements are arranged in rows and columns in the periodic table. A row is called a period, and a column is called a group. There's three groups we need to be aware of the names of. That's group 1, the alkali metals, group 7, the halogens, and also group 8, sometimes called group 0, which are the noble gases. Starting off with melting points and boiling points, these vary periodically in a regular pattern throughout the periodic table, and these depend on the strengths of forces between particles that make up a substance. Strong forces between particles would give you a high melting point and boiling point, and weak forces between particles would give you a low melting point and boiling point. We can look at the way that it varies across the periods, which would be it increases to group 4 and then it hugely decreases. And we've also got, as you go down a group, for groups 1 through 4, they decrease as you go along. And then you also have for groups 5 to 8, they increase. You can see these on page number 6 in the data booklet, and you can just see the trends that I have talked about. Next, we'll talk about covalent radii. Covalent radii is a measure of the size of an atom. We're going to look at how it changes going across a period in terms of the nuclear charge. And also we're going to look at going down a group in terms of the number of occupied shells, and also link that to shielding or screening effect. If you start going across the period, the covalent radius decreases because atoms have more protons in their nucleus. This increased nuclear charge exerts a greater force on the electron shells and pulls them closer to the nucleus. As we go down a group, we're going to have the radius is going to increase because there's more energy shells of electrons. These extra electron shells shield the outer electrons from the protons, and this allows the electrons to be further from the nucleus. We'll now look at some exam questions about covalent radii. The first one is just a simple, what is the trend in covalent radii as the atomic number of the halogens increases? What we'll need to know is that the halogens are group 7. We go to the correct page in the data booklet, and we can see that as we go down the group, the size increases. And for this one, we just have to state what the trend is. As we move on to our second question, which is asking you to compare the covalent radius of sulfur and phosphorus. These are in the same period, therefore our answer has to be in terms of protons and nuclear charge or nuclear pull. And what we can say is that sulfur has a larger number of protons, therefore the electrons are pulled closer to the nucleus. Next, we'll look at ionization energy, which is a measure of the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. We can be asked to write equations that represent different ionization energies. These are given in the data booklet, and it uses the letter E just to represent any element. So in our first one, we have going from E with no charge into a positive ion, and there's an electron being given off. What we might be asked to do is to write one of the equations for a particular element. If, for instance, you were asked about the first ionization energy of carbon, we just substitute in a C where we have a capital E, and that's what we would get. So data booklet, best place to go to help us out. Again, we're going to look at going across a period and explaining the trends that we've got. The first ionization energy increases because we've got an increased nuclear pull. That's more protons, increased nuclear charge. There's more protons in the centre pulling on the electrons, so we have a stronger pull from the nucleus, and the electrons are harder to remove. As we go down the group, we're going to again talk about these extra electron shells, and we're going to look at what happens. So as we go down the group, the first ionization energy decreases because the outer electrons are shielded by the extra electron shells. the attraction of the nucleus, protons, for those outer electrons is going to be decreased. Therefore, these electrons will be easier to remove. In terms of what kind of questions we can get for this, you can be asked to identify which equation represents, in this case, the first ionization energy of fluorine. When we go to the data booklet tells us that E going to E plus an electron is the equation for this, and all we have to do is substitute in F instead of E, and we get our answer of C. The second type of question that they could ask you could be for a higher ionization, so in this case being the third. And if we go step by step, we can see that, well, the first ionization energy would be Al going to Al plus, the second one from Al plus to Al2 plus, and then the third, which we care about, Al2 plus going to Al3 plus, which gives us our correct answer of B. Another type of question they can ask you to do is to look at the ionization energies of a particular element and identify something about it. In this question, we want to know which group this element belongs to. Now, one way of doing it is just to look at the data booklet. Now, from the graph, what we can see is that the first three are fairly close together, and then there's a large jump between the third and the fourth ionization energies. And if we look at some examples in the data booklet, boron fits that category, and boron is in group number 3. Another way we can think about it is that the first three ionization energies are all quite similar. This is because they come from the same energy shell, and the fourth one must come from one which is closer to the nucleus. So group 3 would have 3 outer electrons, which we need to remove, and the fourth one would be more difficult to remove. Next type of question could ask you to explain why the first ionization energy of potassium is smaller than that of chlorine. When we look in the data booklet, we'll see that these are in different periods, meaning they've got a different number of occupied electron shells. Potassium has more shells, and these extra inner shells will shield the outer electrons. And as a result, the attraction of the nucleus for these outer electrons decreases, and it requires less energy to remove. The next property we could be asked about is electronegativity, and this is a measure of the attraction an atom involved in a bond has for the electrons in the bond. And what this allows us to do is it allows us to predict whether the electrons will be closer to one atom or the other. These are found in the data booklet, just beside the ionization energies, and they have higher numbers if they have a greater attraction for the bonding electrons. So in the case of carbon and hydrogen, carbon has a higher electronegativity, therefore the electrons will be drawn closer towards the carbon. In terms of how this trends across the period, they're going to increase because we've got an increased nuclear pool. So the extra protons is going to allow it to pull on the shared pair of electrons more strongly. So that stronger pull from the nucleus, and then therefore there's a greater attraction for these bonding electrons. If we talk about a group, the values decrease as you go down because the outer electrons are shielded by these extra energy shells. That results in a weaker pull from the nucleus and a lower attraction for the bonding electrons. In terms of the questions that we could be asked, they could ask you which of the following has the greatest attraction for bonding electrons. What we need to recognise is that it's just talking about electronegativities. We then go to the data booklet and we look at the values that each of these have, and then we can say that the chlorine with the highest value has the greatest attraction for bonding electrons. Another way they can ask about is they can ask about the trend across the period going from lithium to fluorine. Because we're in the same period, the answer should talk about protons and nuclear charge. We have increasing number of protons, or increasing charge, or decreasing atomic size. Next type of question, we're now going down a group, down group 1 from lithium to cesium, and it tells us that the electronegativity decreases. And this time we have to explain clearly why the electronegativity of the elements decreases. So we need to add more detail to this answer. What we need to include in our answer is that because we're going down a group, We're talking about number of electron shells. And we've got more electron shells as we go down. So the outer electrons are shielded by the extra energy shells, and there's a weaker pull from the nucleus, therefore a lower attraction for the bonding electrons. Hopefully now you've gained a clearer understanding of the trends in melting points and boiling points, the trends in covalent radii, trends in ionization energy, and the trends in electronegativity. Thank you for watching. Goodbye.